In this video, I'm going to recap topics from quarter 2 for trig. Mainly, I'm going to focus on chapters 5 and 6. Chapter 5 was all about identities and verifications. So you'll see here all of the different identities we learned. The first set are reciprocal identities. Just talk about which functions are reciprocals of each other. Notice that you will never, ever take the reciprocal of an angle. You are only taking the reciprocal of a ratio. Secondly, we have our quotient identities. Quotient means division, and so these are the two identities that are a quotient or division problem of the other. Our Pythagorean identities are all derived from the x squared plus y squared equals r squared. So if you forget them, you can start with that statement and first divide everything by x squared, then divide everything by y squared, then divide everything by r squared. So those are those identities. The negative angle identities, basically for every function except for cosine and secant, if you plug in a negative angle, it will equal the opposite of what you had with a regular angle. So the way that we talked about this in class was if we have cosine or secant, the negative makes no difference. For everything else, the negative puts a negative on the outside. When we're doing verifications and simplifying, first of all, remember the final is multiple choice. So you need to be able to recognize the correct answer. Some different tips are to work on the more complicated side because it's easier to make it simple than it is to take a simple side and make it hard. We're going to do a lot of substitutions with our identities. Sometimes it's helpful to rewrite things in terms of sine and cosine. This can be useful since every function can be written in terms of sine and cosine. Sometimes things will cancel or you'll be able to combine fractions easier. Other techniques that we used are factoring, foiling, making like denominators and adding fractions, distributing, and then lastly we talked about using conjugates. Conjugates are useful when you see, for example, 1 plus sine x. If you multiply by 1 minus sine x over 1 minus sine x within a fraction, then you get those Pythagorean identities which we can use with substitutions. We had a lot of examples in this chapter, so I'm not really going to do a whole lot of problems here. What I would suggest is to go back and look at your chapter 5 worksheets and just redo some of the problems. Our sum and difference identities for tangent, sine and cosine. This symbol here, we've talked about this in class, the plus minus minus plus, basically just shows that for the cosine formula, the sign switches, and for sine, the formula, the sign stays the same. Again, we need to know all of these formulas, a lot of memorization on this final. These are our double angle identities. Cosine has 3 formats of this formula, and the way that we derived them, if you recall, was we started with cosine of a plus a, and we worked out the first formula. And then once we had the first formula, we just did a substitution using the identity of the Pythagorean identity. So if you forget those, that's how you can derive those. Same thing is true for sine and tangent double angle. Alright, so here's an example of a problem that we might ask you to solve. In this problem, the first thing that jumps out at me are the double angles, and so I would replace these with our identities. So we would have cosine x times sine double x is going to equal 2 sine x cosine x. And then denominator, I have 1 plus cosine 2x. If I simplify this numerator, I get 2 sine x cosine squared x. So looking at that, I need to try to figure out what would be the best version of this formula to replace with. And the version that I'm going to use is going to be the 2 cosine squared x minus 1. The reason why I'm going to use that one is because then the minus 1 and the plus 1 will cancel, and then the cosine squared x's will cancel as well. So this is going to be 1 plus, here, 2 cosine squared x minus 1. Now the minus and the plus cancel, and I am left with 2 sine x cosine squared x over 2 cosine squared x. Cosine squareds cancels, 2's cancel, and we are left with just sine of x. in this problem, what we want you to recognize is that cofunctions are equal if angles are complementary. Complementary means that they add to 90 degrees. So we can say 5 theta minus 1 plus 3 theta plus 19 equals 90 degrees, and then we can solve from here. And we find out that theta equals 9. Alright, in these two problems, we want you to recognize in the top one that this is an expanded version of our cosine sum formula, and we want you to put it back together again. So recognize this as cosine A cosine B minus sine A sine B is really just cosine of A plus B. So this is my A, this is my B, therefore this can condense into cosine of 112.5 plus 22.5, which is cosine of 135. And at 135, cosine is equal to negative root 2 over 2. In this second problem, 75 degrees is not on our unit circle. However, we could rewrite this as cosine of 45 degrees plus 30 degrees. And you'll recall we did problems like this for sine, cosine, and tangent. So the principle is the same regardless of which function it is. So then this would give me cosine 45, cosine 30, minus sine 45, sine 30, and then from here I just plug in the unit circle values, which again we should know by heart by now. And there's my answer. Alright, so here we have two different angles, angle A and B. What we talked about in class is first finding the XYR values for these two angles. So for angle A, if we know that sine is 3/5, then that tells me that my Y value is 3 and my R value is 5. For angle B, we know that cosine is negative 12/13, so X is negative 12, R is 13. This information here tells me that angle A is in quadrant 2 and angle B is in quadrant 3. And that's useful because we know that for angle A, X is negative, and for angle B, both X and Y are negative. We can now fill in the missing values using our Pythagorean triples. Now that we know our XYRs, we can expand with our formula. My sine sum formula is sine A cosine B plus cosine A sine B. So now I can go ahead and just plug in those values. Sine A is 3/5, cosine B is negative 12/13, cosine A is negative 4/5, sine B negative 5/13, giving me negative 36 plus 20 over 65, so negative 16 over 65. In this problem, this is a verification. Now again, your final is multiple choice. However, we might ask you what this simplifies to. So I figure this would be a good example to just recap some of our principles that we've learned. In this problem, I'm going to work the right side. So first I would distribute the squared, giving me tan squared x, sine squared x. Then I'm going to do a substitution. I'm going to replace sine squared x using my Pythagorean identity. Remember that sine squared x plus cosine squared x equals 1, so I can replace sine squared x with 1 minus cosine squared x. And we did substitutions like this quite a bit in class. From here I'm going to distribute tangent squared x minus tangent squared x cosine squared x. Now I'm almost there, however, this right side does not match that right side. And at this point I recall my quotient identity, and my quotient identity says that tangent is equal to sine over cosine. So I can rewrite this as sine squared over cosine squared, and then voila, my cosines cancel, and now I have tangent squared x minus sine squared x, and we have verified. Okay, in Chapter 6, we started learning about our inverse functions. One of the key things that we talked about was that the domain for an inverse is a ratio, and the range is an angle. This is because when we talk about our inverse functions, the domains and ranges switch. So you'll notice when we look at sine and cosine that these domains are ratios between -1 and 1, because those are the only possible ratio values for sine and cosine. Tangent and cotangent can be anything, and secant and cosecant are only greater than 1 or less than -1. Then when we look at our angle restrictions, we talked about how sine, its inverse, and tangent are all in quadrants 1 and 4. And when we say quadrants 1 and 4, what we really mean are negative angles in quadrants 4, like negative pi thirds and negative pi fourths and negative pi sixths. Okay? Your cosine, its reciprocal, and cotangent are all in quadrants 1 and 2, which means all of the angles here on the top. When we are doing a basic inverse evaluation, if there is no equation and there is nothing telling us our answer has to be between 0 and 360, then we have to remember these restrictions. So for example, this first problem is saying at which angle is there a cosecant ratio of 2 root 3 over 3. Cosecant has a restriction in these two quadrants. So because it's positive, I'm going to think of when does sine equal root 3 over 2, and that happens right here at pi thirds. This next one, arctan, that's the same as saying tan inverse of negative root 3, and tangent has the same restrictions as cosecant. Tangent is negative down here in quadrant 3, again, or quadrant 4. Again, we can't give this answer as 5 pi thirds. We have to give it as negative pi thirds or negative 60 degrees because we are following those restrictions. Secant, for this you want to think of cosine. When does cosine equal -1/2? And that's going to happen at 2 pi thirds. These next two problems, we want to work from the inside out. So first, it says cosine of 7 pi 6. So since my input is an angle, my output is a ratio. And 7 pi 6 is right here, and at that angle, the cosine ratio is negative root 3 over 2. So now my problem becomes cosine inverse of negative root 3 over 2. However, because I'm now doing a cosine inverse, I have to obey those restrictions. And those restrictions tell me that my answer can only be in quadrants 1 or 2. Therefore, my answer is 5 pi 6. So I don't want you to assume that a cosine inverse always just cancels off a cosine. We have to actually walk through the problem. And then for this last problem here, when we see this, anytime we see arctan of a ratio or tan inverse of a ratio, this answer is equal to an angle. So this really comes down to sine of 2 times an angle. And we don't know what the angle is, and we really don't care. We just want to figure out its x, y, r values. Based on what we know that the y is -12 and the x is 5. We know it's negative. Why? Because if tangent is negative, it has to be down in quadrant 4, because tangent goes from negative pi halves to pi halves, meaning that the y has to be negative. We know that r is 13 because of our triples. So now I can simply expand this using my identities and plug in. I know that sine is y to r, so I'll have -12 over 13. Cosine is 5 over 13. And then if I multiply this through, I get -120 over 169. When we are solving, there's a lot of things we want to think about. Most commonly, we isolate the trig function. A lot of times we will factor, square both sides. If we square both sides, you have to remember to check your answers. We can also rewrite using our identities. And a big thing to remember is that you cannot divide away a trig function. If there is something that is common to both sides, you want to factor it out. So instead, you want to factor it out as a GCF. That was a common mistake students made in this chapter. Alright, when we look at the first problem, we're being asked to solve for sine, and this is a quadratic, so we would automatically think to factor. This is going to factor following normal factoring patterns for quadratics. We know we'll have a 3 sine x and a sine x. We know we're going to have a 2 and a 1 on the outside. And here's where everything fits to make it factor correctly. So at this point, now we're going to set each of these parentheses equal to 0. 3 sine x plus 1 equals 0, and sine x minus 2 equals 0. Now, on the right-hand side, this one is impossible. Sine can never equal 2. Since it's not possible, it doesn't result in any solutions. However, the left-hand side is still doable. We are told that we want to solve in 0 to 360, so we want to make sure our calculator is in degree modes. And now we're going to do sine inverse of negative 1/3. Now, when I type this in my calculator is going to give me this answer, negative 19.47. It gives me this answer because the calculator knows that the restrictions have to go from negative 90 to 90. However, I'm asking you to give me an answer from 0 to 360. So we want to visualize this reference angle is 19 degrees below the axis in quadrants 3 and 4. So that means that my answers for x are going to be 180 plus this 19 decimal and 360 minus this 19 decimal, giving me 199.471 degrees and 340.53 degrees. For the problem on the right-hand side, we want to go ahead and isolate our tangent function. Since there's only one function here, we can go ahead and isolate it easily. So 6 tan theta equals negative 2 root 3 divided by 6. And we get tan theta equals negative root 3 over 3. Again, we are in degrees. So tangent is negative in quadrants 2 and 4. And this will happen at 150 degrees and 330 degrees. Alright, sometimes our angle will be halved or multiplied. So you might see a 2 theta or a 3 theta or an x halves, theta halves. When this happens, we have to adjust our interval. So if we see an x halves, we have to divide our interval by 2. If we see a 2 theta or a 3 theta, we have to multiply our interval by 2 or by 3. That will allow us to go around the circle more times or not go around the circle as much. Once we get all of those solutions, then we have to fix the answers by either multiplying or dividing accordingly. Let's first look at a problem with an x halves. So here I'm going to isolate the cosine, and I get cosine of x halves equals 1/2. Since my variable has been divided by 2, my interval needs to be divided by 2 as well. Whoa, that's really sloppy. So this is my new interval. So now I ask myself, okay, well, when does cosine equal 1/2? Well, normally I have an answer in quadrant 1 and 4. However, quadrant 4 is no longer in my interval, so I can only use my answer that's in quadrant 1, and this occurs at pi thirds. So right now I know that x halves equals pi thirds. So this is what I mean when I say adjust my interval. Now I need to fix my answers. This is my answer for x halves. I want to know the answer for x. The answer for x is 2 pi thirds. Now I am done. If we look at the second problem, sine of 3 theta equals root 2 over 2. Since my theta has been tripled, my interval has to be tripled. So now this goes to 6 pi, which means it's 3 times around the circle. So I ask myself, when does sine equal root 2 over 2? And that happens at pi fourths and 3 pi fourths. So right now I'm going to say 3 theta equals pi fourths and 3 pi fourths. And then now I need to go around the circle again. So I'm going to add multiples of 2 pi, or in this case 8 pi fourths, to each of these answers. So that will give me 9 pi-fourths and 11 pi-fourths. And then I'm going to go around the circle one more time. 17 pi-fourths and 19 pi-fourths. Now these answers are all equal to 3 theta. Since I want my answer to equal theta, I have to divide all these answers by 3. And then we want to give our answers in reduced terms. And voila. Alright, lastly, don't forget Chapter 7. I'm not going to recap all this. We are testing on this right now. However, law of sines, law of cosines, don't forget your bearings, vectors. Study, study, study. Hopefully this was helpful. Good luck, guys.